All right, thank you everyone for coming. Welcome to the April APUG. We have a lot of fun things in store today, and first off, I'd like to thank our sponsors. As always, Capital Factory is very kind to provide us the space, and also parking validation. So now we're validated as a meetup and as individuals. Those who don't know, who don't see all the emails I send out, we can get $5 parking in the Omni right here. We have to pull in after 6, but then you get a validation ticket from Ollie up there. He's got his hand raised. Also, for beer and pizza tonight, our sponsor is unable to actually come and, well, I don't think they were able to make it to actually speak. So they sent me a slide, and they will come next month and do a brief blurb. But they are Steep Rock, and as you can see from the slide, they are hiring expert Python programmers, a bunch of devs. The guys seem really nice. I haven't met him yet, but I'll meet him next week or next month. But anyway, I would highly encourage, if any of you are looking for a new position, if any of you know people, that's the other important thing. Think about your friends, think about your colleagues who are stuck in bad jobs. If you know someone who might be interested in a position like this, please email them this opportunity, steeprockinc.com. And also, as with any of the things you find out about through APUG, please mention to them that you are grateful for their sponsorship of APUG. That's what keeps people kind of sponsoring us on a recurring basis. Additionally, if your company is looking to hire, and if you're interested in sponsoring, we have actually a sponsor prospectus now. And if your company is willing to sponsor, say, a block of up to 4 meetups over the course of a year, there's additional sort of mentions and things that we'll basically hand out as sponsor benefits. So please get in touch with me about that. One of the other things is, I unfortunately didn't get put together for this month, but that's in the works, is that JetBrains is going to be giving us sort of like a free code to give out at each of our meetups, I think, for a couple of their tools. So that's in process. And also, we have great links with O'Reilly Media, so if there are any O'Reilly books that you guys would really like to get for free, we can't get all of them for everyone, but if they're like a couple, shoot me an email, and I can bounce over to them, and it'll take a little bit to get a round trip. But if it's an ebook, something like that, we can work through those sorts of things. So definitely keep those in mind. We are quite visible meetup, and a lot of people are interested in providing us perks of that nature, so definitely keep that in mind. As I was saying earlier, the pizza will show up at 7:30, which means that we have, well, maybe a little bit after 7:30. But Chris is going to be giving us a presentation that's going to be about a 15-20 minute presentation, right? And then we'll break for pizza, and then we'll have an additional presentation or 2 after that. And then we'll try to do this just a social event and kind of show and tell kind of thing. So again, thanks. Round of applause for Capital Factory, for Steep Rock, for our sponsors. And Chris, I'll turn it over to you.
Any idea how to get it over to this?
I'm afraid to touch any buttons. Do I sit on the mic? Okay.
Maybe here? I think it's connected.
That's the lab size.
Oh.
There's another remote.
Make sure I'm pretty sure it's connected, so.
Yeah, it sees the other device. It's just getting that device to acknowledge the input. Now I'm going to turn this off. While we're getting the setup, actually, if you want to put on a USB stick, I can put it on mine too. It's just a PowerPoint.
There's videos and stuff.
Videos, okay.
Yeah.
How many people here are going to PyCon? Woo! Really? Just the 2 of us?
You're still in town.
Oh.
All the other ones are already there.
Oh, right. That's how many people here are already at PyCon? No, sorry, not true, John. The data disproves your point.
No.
Hold on. We're getting AV help.
AV folks.
Only one can go.
So I'm plugging in through the HDMI.
You there?
Yeah.
I got it. But it didn't fly.
Oh, Something happened. Maybe your display.
Is the screen size set too high?
There we go.
Oh, fantastic. All right. Thank you so much. We can move the podium, right? There are, yeah.
So whenever you switch, whenever that floods, it's gonna switch again.
Okay. This is probably like 20 minutes.
Okay, so I'll hang around here.
I mean, we can just hit the button, right?
Sure. Two things you need to know. What is that? I'll move you to the next one.
Okay.
There we go. And when you see it, that's the one that's on. The switch moves the input.
I see. Oh, you're still I see. Input 2 for the HDMI.
And input 1 for Apple TV.
Got it. Okay, thank you. All right.
It doesn't like it when I go to full screen. One second.
Yeah, maybe your resolution's too high.
It should be. It's all this is.
Yeah, it doesn't like that.
All right. Any idea what it is?
Can you just hit the maximum maximize button? So just mirror displays and then just maximize this so full screen.
I can turn on the resolution. Well, maybe I can.
You know about
Hey.
Okay. All right, here you go.
There we go. Sorry about that. Hi, so my name is Chris Lindner. I'm a PhD candidate over at the University of Texas here in Austin. I'm in the Department of Astronomy. I'm going to talk a bit today about my research and talk about how it applies or where we use Python in it.
everywhere.
Not everywhere, but we'll talk about why not, and you guys can tell me if these are good or bad reasons. So real quickly, it's exactly what we're going to talk about. Talk about my research a little bit, then we're going to talk about where I actually use Python in my simulations, and then I'm going to talk about where Python doesn't get used in a lot of science. As it turns out, we don't use Python that much, and what our common objections are, and you guys can sort of comment on if you think those are legitimate objections or not. All right, so I study exploding stars, otherwise known as supernovae. And basically what we think happens is we see these big, bright explosions in the sky. We either see them through our telescopes, or occasionally you can even see them by the naked eye. These big, bright things, they look like new stars, very bright explosions in the sky. And so we think these are the explosions of very, very, very massive stars. And so it's my job to kind of understand why these things explode. We know at the end of life of a massive star, the core of that star will actually get denser and denser and denser until it collapses into a black hole. And unlike what you might have heard of from one of the recent Star Trek movies, that does not cause that star to just collapse and get sucked into the black hole. Instead, we know when you actually form a black hole in the center of a star, for whatever reason, that star then explodes, and explodes very magnificently. And so I try to work out the physics and understand why it is that these things explode. So the first thing you gotta understand is when stuff falls towards a black hole, as it falls towards the black hole, if it has any sort of angular momentum, it'll form a nice little disk around it. And inside of that disk, it can rub up against each other and get very hot and very energetic and basically generate just a whole lot of energy inside of this accretion disk. And we think there are ways that you can then carry energy away from that accretion disk into the surrounding media and possibly cause an explosion. So the first thing I'm going to show you here is a simulation I've done of basically material from a disk falling into a black hole. And what you're going to see, this is just our pink little donut here, is a donut of material around a black hole that's in the center here that you can't see the black hole there. And you're going to see the material fall in, and then you're going to see sort of an explosion of matter coming out, not coming out of the black hole, but instead it's material that just sort of misses the black hole and gets flung out by all the energy that's going on there. You're also going to see some lines that are magnetic field lines. Don't worry about those. I won't talk about those today.
Why?
Complicated. All right, so stuff's starting to fall in, boom. You get this giant explosion here. And so like I said, those little lines are just magnetic field lines, but basically material is being thrown off, energy is being thrown off Most of the material still ends up falling into the black hole itself. But even if you can extract just a little bit of energy, 1% of the energy from the material that's falling into the black hole, that's enough to make these giant explosions that we see. So we think most of the material inside of this black hole is that's falling towards this black hole is just gonna fall right in there. But a little bit of it's gonna get out, it's gonna carry away some energy, maybe it'll shoot off some big jets like we're seeing here, and that could drive some sort of explosion. Now, we see these supernovae all the time. Most of the time we have to just observe them through telescopes, but historically there have been supernovae that have been visible to the naked eye. For example, there's a very famous nebula called the Crab Nebula. And this is what it looked like in 1054, and this is what it looks like today in 2005. So in 1054, of course, we didn't have any telescopes, but many different ancient cultures actually recorded seeing a new star in the sky, some really bright object. So bright, I mean, you could see it at night. You could see it was brighter than Venus would be in the night sky. And this petroglyph right here shows, here's the moon, and a hand's length away from the moon, there's this star. So they kind of just held their hand up and they see, here's where this new star is located. Then we pointed the Hubble telescope there in 2005, and we see this right here. This is what we call the Crab Nebula, and it's basically the aftermath of the giant explosion of the star. As the material runs into all the gas and dust surrounding it, it creates this very beautiful picture that we see. It creates lots of X-rays, lots of energy, all sorts of neat, nice things that we see from there. All right, so what's going on here? So what I showed you before was just a black hole on its own with a little bit of disk of material around it. But now we're talking about black holes that are inside of stars. How does that make the star blow up? So I want to study this by using big, multidimensional simulations. And I want to see what happens if you put all the physics in that we know about into this thing. You take a star, what we think stars are like just before we die, and you drop a black hole in the middle. What happens? And so I'm going to show you a video of one of my simulations. And basically what you're seeing is a slice of the star. The colors represent the density. So here in the center of the star, it's very dense, and it's less and less dense as you go out further and further. And what's going to happen is most of the material is going to start falling into the black hole. You're just going to see sort of this collapse. But all of a sudden, at some point, some of that material is going to have enough angular momentum, and it's going to start to form a disk. And when that happens, you'll see a shock wave spread out through the star, and then you'll actually start to see all this energy that's being generated in the disk. There will be some material being carried away and some energy being carried away from that disk region. And we think it's by extracting energy from this accretion disk that you get a big explosion.
How big is this star, by the way?
This would be like this is a 20 solar mass star, so 20 times the mass of our sun. So our sun will not do this. So there we saw the collapse. Now we have this accretion disk. There's some sort of black hole, little black hole in the center there. This is sort of our disk of material. And you can see material is kind of getting carried away. This is just sort of convection, basically taking all the energy that's being generated really close to this black hole, carrying it away, carrying it out. The surface of the star is a little bit further out here, but all that energy is being carried out to the surface of the star where it can cause this explosion. We can't see this part of what's going on with our telescopes, but we can see the explosion on the outside. And it turns out when I do these simulations, the energies that I predict from my simulations and the composition, meaning what elements the explosive stuff is made out of, that my simulations predict is exactly what we observe. So basically we think this is a good model for what's happening when we see these big explosions in the sky. Yes?
How much time is elapsing with this video?
This movie is actually in real time. So it shows about 100 seconds of evolution, and that would be 100 seconds of evolution in the star. So supernovae are really cool things because this star lived for tens of millions of years, and then all of a sudden its life ended on a scale of hundreds of seconds. Yes?
Am I correct in saying that we're really looking at like half of this and then the other half is mirrored?
Yeah, I've mirrored it because, the geometry is such that it's just a sort of a pie shape. So, this is just a two-dimensional simulation here that I'm showing you. All right. So that's the science. So how do we do all of this stuff? Well, I use a code called the Flash Hydrodynamics code. It's a pretty big code, 300,000 line, open source, massively parallel fluid dynamics code. I use open source in quotations. It's one of the first codes that's really freely available to just about any scientist. However, because these types of codes can also be used for some nefarious things like designing nuclear weapons, they don't want to give it out to just anybody. But if you're an American scientist, at least, you can get your hands on it pretty easily. It's a massively parallel fluid dynamics code, and it's just sort of, and we use it both for astrophysics, so the type of stuff I study, but it's also used in a lot of high energy physics, so things like the fusion experiments that they're going on at fusion power plants, or any sort of laser experiments that they're doing, they also use this same code. It's a very versatile code. Now, the bulk of the computational code is written in Fortran 90. Yes, we still use Fortran.
Fortran for the win.
Yes, it is quite a language, and I'll talk a little bit more about why we use that. But you can see my sad face there expressing my feelings towards using Fortran 90. There's some initialization and analysis written in Python, which I'll talk about a bit. There's also some code that's written in C. Some of the physics and some of the input-output is written in C. We use a language called IDL that probably most of you have never even heard of. Oh, we got someone excited about it back there. All right, all right. We use a little bit of that for data analysis. And so the production runs for like the simulations I was showing you would be somewhere between 100,000 and 10 million CPU hours. So obviously we can't run this on local machines. We have to use supercomputers. Luckily here in Austin, we have one of the world's biggest supercomputers. Stampede is a 500,000 core supercomputer located here in Austin, and it's supposed to be the 7th fastest in the world, or 7th fastest one that we know about, at least, in the world. So it's kind of hell to work in all these different languages. This code is kind of a mismatch of a lot of different things. And so on a typical day, there are some days where I've got about 5 or 6 windows open, all in different languages. And it's fun to go and have to change something in this file, then try to remember, oh, what's the comment character in whatever language I'm using? Oh, what's the loop structure? Switching back and forth is kind of a mess. But basically, yeah, I mean, there are times where you have to work in all the different languages at once, and then you get it down here to your end where you're using this Python-driven visualization. So what are we using Python for? Well, the first thing we use it for is to set up our code. So basically, it does a lot of the initial setup before we actually compile the code. First, it's going to decide which Fortran or C physics modules we want to use. So basically, this is a versatile code. It's got a lot of different physics units in it, so you can decide, do I want to use magnetic fields in my simulation or don't I? Do I want to include radiation, hydrodynamics, or don't I? You basically type all that in, and it decides, okay, these are the source files you need for that. But before that, it double checks and makes sure that all those source files are compatible with each other, goes through and sets all that up, and then it creates one big directory for you where it creates symbolic links to all the different pieces of code you're using. And this is kind of convenient so that you can go through then and just, you have one directory where you know this is a piece of code that it's actually running. I can edit any file in there and make it really easy. So, and then it generates our make files. It determines what type of system you're on, and then sets up for that system, tells it where all the libraries are, all that good stuff. So Python, you've probably seen it before, install scripts written in Pythons for various different things, but it's very useful here, very nifty thing for us to use here. The other place we use it is in our visualization and our data analysis. So all the videos I showed you earlier here were done in Visit, which Visit is an open source visualization package we have. Basically, it's written in C, Python, and Java, but you can actually write Python scripts to control it. So generally, the way you would use it is you could go through and you could use this nice graphical interface. But if you want to do something like generate a movie where you're going to generate 1,000 frames, you don't want to have to go back and set up each frame one by one by one. So you can write nice little Python scripts, and the language interfaces with those very nicely. You can basically do all the same things you could do in the graphical user interface. You can do that all in Python here. Kind of on the cutting edge is YT is sort of a new visualization package that's come out, and this one's written totally in Python, which is kind of nice. It's an open source data analysis package. Does the same sort of things as Visit, but it actually has a lot more tools, a lot more power to it, a lot easier to change things in there. And it uses a lot of the very modern Python packages that you guys are familiar with. So it uses Cython in order to interface with C, NumPy for all its array functionality, matplotlib to actually do the nice display, H5Py uses we use a data type called HDF5 is how we store our big data files. and so that lets us access it. And MPI for Pi, you can do this in parallel. Visit you can also do in parallel as well. But you can basically do your data processing in parallel, which is important when you're working with data files that can be tens or hundreds of gigabytes. And basically then what you're seeing down here is a couple of visualizations. One cool thing is YT, they've tried to make it useful for all types of scientists. And so you can see on the left there, this is actually something from medical science where they did an MRI scan of a skull, and they're visualizing the data using YT. And on the right, you're seeing stellar formation / supernova happening in the early universe type simulation. And they've made some very pretty animations for using YT. So we use Python at the beginning, we use Python at the end, but the bulk of our work, the bulk of what those supercomputers are churning away at is done using Fortran. So why don't we go to a more advanced language like Python, or at least Java, or something C++, something object-oriented. So these are the excuses I hear, and I don't necessarily agree with all of them, but if you want to know why science doesn't use them, I think it really boils down to these. The first complaint I always hear is, well, it's too slow to use anything else. If you try to use Python for these types of calculations, it's going to be way too slow. We say, well, the calculations, take 10 times as long in Python. Even to do a simple math operation, it's going to take 10 times as long to do it in Python versus C. But the first thing I would say is, well, you really have to compare man hours versus CPU hours. It's much easier to edit Python code. So even if you have to waste additional CPU hours, it's kind of nice to have a code that's really, really easy. My time is way more valuable than a computer time.
Wait. Grad student time is not a man hour.
This is true. Yes, not, people don't agree. We'll get to that in the fourth point there. And then the second point is, there's actually a lot of nice packages now in Python. It may have been true back in the day that, yeah, you can't make Python fast, but there's lots of people now working on making Python very fast and very parallel and very useful. So I don't think that's necessarily true anymore, but this is still what's in most people's minds. And so even in other languages like Java or C++, a lot of scientists will say the same thing. They'll say, oh, those are too slow, there's no way we can use them for this. And really, they're just not very familiar, I think, with the cutting edge of any of these languages. Similarly, on the second note, a lot of people say, well, they don't have the libraries we need. We use libraries like GSL, which is sort of a science math library, does a lot of very fast solvers and those sorts of things, linear equation solvers. Hyper is a very parallel linear equation solver, matrix operation library, and MPI. And so, this was probably true of Python, 7, 8 years ago, that it didn't have these packages, but I think most people in this room know, well, nowadays Python's been extended to have sort of all of these things, or different versions of these things. We know we have NumPy and those sorts of things that can do very fast matrices operations. We have MPI now for Python, so you can do everything in parallel. So I don't think it's necessarily true, but I think it's, again, a misconception that hangs around the science community. And then the last 2 points, the last 2 reasons that we use our Fortran as opposed to Python. I mean, first of all, is there is this legacy code. There is code in Flash, even though it's a code that's technically, maybe 10 years old, there's code in there that's 20, 30 years old that's been passed down and passed down and passed down, and nobody wants to mess with it. And so it just hangs around forever. And it's very poorly documented, as you would expect, and very archaic, and just everybody knows it works, so they don't want to touch it. And then the last reason is legacy professors. The movers and drivers are not graduate students like me, unfortunately. We all have to work under professors who never learned C++, never learned Python, never learned these languages. And so if you hand them some file that's in some language they don't understand, they're not going to want to use them. They're going to tell you to rewrite it in Fortran. So we are woefully stuck behind. I think people, though, are starting to get the message. I think YT is really cool, and that was something that was started by a bunch of graduate students who were sick and tired of using the old school tools, wanted to do something more advanced and all that. And I think down the road we'll see more codes like this being used in higher level languages and those sorts of things. So that's about what I got for you. In summary, big stars form black holes in their cores, and those make them blow up. I simulate those explosions. Other astrophysicists simulate those explosions on supercomputers. Fortran and C are used for about everything. Python is used to handle a problem setup and also for our data analysis. And modern tools now might enable us to start using some of these other higher level languages for this kind of stuff. And I think we're starting to see a push for that. And then finally, I'll say, I'm graduating soon, leaving astronomy, so please, if you are interested in a data scientist here in Austin, I'm looking for those types of jobs. I have lots of experience in lots of different languages, so ask me about it, or just come talk to me after the talk too. I'll show you, I've got some movie with 3D glasses, a version of those previous ones, so I can show you some cool things too. And people have questions. Yes?
You had a picture of a supercomputer with 500,000 cores. So what kind of utilization does something like that get? I mean, is it busy all the time and you have to queue for
Yes, sort of. So yeah, it's hooked into, there's sort of a national collaboration with all these supercomputers, and they get a lot of federal money. So it's not just UT people using it, it's from people across the country, and this is kind of their biggest installation of them all. As far as utilization goes, it really depends on how many CPU hours you want. You know, if I want to do a run that's going to take 100,000 CPU hours, I can probably start it and it'll be finished, you know, in a week or something. You know, I mean, it doesn't take too long to get that run. But if you want an allocation of tens or hundreds of millions of CPU hours, yeah, then you're probably going to have to wait a week or a month and actually tell them, like, I mean, if you're running on, you know, 50,000 processors or something like that, you're going to have to talk to them ahead of time and be like, okay, you need to reserve all of this for me, you know, shut down that. But as far as the overall utilization, it is constantly used, and they do a good job with sort of maintaining that and making sure everybody can kind of get a piece of the pie and making sure they divvy it out right so that you don't have to wait too long, while at the same time you can actually get things done.
So who would want to rewrite 300,000 lines of code in Python?
who could? Or?
Who would want to?
Who would want to? I mean, well, so, you know, it's not just Python. I talk about Python because we're here, but I've actually used one code that does similar things towards this, and it's in C++, and it basically never caught on for very similar reasons. People were afraid it was too slow. People were afraid of the higher level functionality. But at the same time, when I used that code, when I wanted to add in a new unit, it took, you know, 10% of the time it would take for me to do this in the same Fortran code. Because being able to program and use higher level functionality, being able to, you know, go in and really be able to, you know, use object-oriented code just turns out to be a million times easier to code, a million times easier to bug check, all that kind of stuff. Just get made, you know, it's a lot easier to use these better codes. Now, who wants to go and rewrite a code from scratch? I certainly don't. It takes, you know, people have done that. I mean, Flash isn't the only code out there. There's about 15 different hydrodynamics codes out there at least. But to write one, it usually takes one person locking themselves in a room for 2 years straight. And I'm not interested in doing that just for the sake of going to Python, but maybe somebody will down the road.
So I'm not familiar with the export restriction on Flash itself, but I mean, wouldn't other governments, the sovereign sort of entities that can't get access to this, I guess they would just engage in espionage to get it, or would they just? Yeah,
I mean, I kind of think it's a bit futile for them to try to hide this code in particular for a number of reasons. I mean, but yeah, I mean, the code is easy enough to get that, you know, all they have to know is one American who's willing to hand it over to them, you know, I mean, if I can get it.
American.
Yeah, I mean, if I can get it, anybody can get it, so, you know. But also because, I mean, there are a lot of these codes, many of them in publicly released, and I assure you, you know, a lot of other nations do have their own codes, and most of the biggest supercomputers, the ones we don't know about, are from other nations with much bigger ones than this, and, you know, doing these types of calculations for nuclear bombs, they clearly have their own codes for these types of things. Yes?
I saw you had GSL and height here, and
yeah.
then you had R. Is there no BLOS usage in Python, or is it just not feasible? Or I'm just kind of curious as to like why you chose those particular linear libraries.
Those are the ones I use in Fortran. So I don't really know. Yeah, and those are the ones that I've just traditionally had access to, and they're the ones that have been used for years and years and years and years and years. You know. Yeah, in the back.
Python?
You know, 2.7. Nobody's using 3. Come on.
It's kind of a weird question, but do you ever use like analogies in other things to explain like stars and stuff like that? Like for example, like you could imagine like the Earth is like an embryo in a womb, which is the universe, and like something like inseminated it, and then there's like and we're like this little embryo, and the internet's starting to form our brain, and I don't know. If you guys use analogies like that for describing stars?
No. No, I mean, it's different when you're doing outreach and stuff, but sometimes you do. I'm not as flowery with my words, no.
So I mean, a lot of these jobs are using multi-gigabyte, maybe even multi-terabyte jobs. Are you guys FedExing hard drives around, or do you have a network that can handle this?
Our network can handle this, yeah. I mean, it's incredibly fast, and as long as you're doing it on site, so you try to use it with your machines on site, it's very, very fast. And so
it sounds like a lot of these people using this are not physically at the supercomputer.
Right, and so actually what they've done recently is they built their own data analysis machine. So in addition to just their standard big bulky supercomputer, they also have clusters that you can reserve just to do data analysis. And so that's kind of the preferred way now, because yeah, you're doing tens or hundreds or gigabytes or terabytes, sending that over across the country is basically impossible. So I think most people who are off-site will just do it, will basically just go ahead and do all their visualization on the machines themselves.
Won't fit on your desktop either.
Yeah, I mean, it won't fit on your desktop, like, depending on how big it is. I mean, some of my simulations I showed today were big enough I could fit them on, like, a local cluster we have, and it was a little easier to do, but some of the stuff's been too big to do that, and yeah, you just got to use their resources. Yes?
What kind of things have you and your team been looking for in the simulations you've been doing?
So the big thing we've been trying to reproduce, we've been trying to answer this model's been around for a while, this idea that, okay, there's this like accretion disk and it blows up this star. But nobody's ever been able to really prove that that produces the energies or the elements that we see. We can, we see these explosions, and based on how bright the explosion is, we can tell you how much energy was in it. And then we can do what we call, spectral analysis, which if you watched Cosmos this week, you learned about analyzing spectra. Yes, so it paid off, right? So so we can use spectral analysis to figure out what that stuff is made out of. And so those were the two big observables for at least this project I was really trying to work on, was trying to be able to see, okay, if we put in all the physics, if everything works the way we think it does, do we get out the answer that we know we need to get? And the answer was yes, at least from my Yes?
Tell us a bit about the process of actually running so much together, because several things happen. There are bugs in the code, small ones that you don't notice at the beginning. So we probably ramp up before we go to the big cluster.
Yeah.
First thing. Second thing is, when you start running with big clusters, sometimes things go bad. I know some CPU stops working or something. What do you do? Tell us the stories behind that.
Yeah. So for the first question, we have a local cluster in the astronomy department, which is basically just some 16-core machines with lots of memory. And so I do all my testing on those, basically. And yeah, you do need to just ramp it up and ramp it up. Especially if you're working with a totally new code, or if you've changed a lot, you really have to do a ton of tests. And so a lot of time you'll apply for CPU time just to do scaling tests, because they're not going to give you 1 million CPU hours if they think you're over or under predicting, how much time you're really going to take. If your simulation is going to take 10 million CPU hours, they don't want to give you 1 million CPU hours for you to burn. So you spend a lot of time seeing how long is this going to take, how well does this scale, and you do a lot of small scale simulations. You also try to do, in any final one that you're going to publish, you have to actually publish, here's a lower resolution simulation, here's a higher resolution simulation. They give the same answer, so I know I've hit sort of the resolution limit. There's some dicey ideas in there, but you try to at least prove it. Your other question, what if something goes bad on the supercomputer while you're running?
Happens.
Yeah, it does happen. I think the highest number of processors I've run on is 1,000, and so, or 1024. So I haven't had to worry about that as much. If it fails, I just tell them to restart it, and they'll restart it again. And you're kind of dumping restart files as you go along, so it can restart pretty easily. But I know for some of the bigger calculations, they do actually, if you're running on, 100,000 processors at once, then your likelihood is an order of magnitude more of something going wrong, and it can be a big deal. And so I know there are, codes that try to do error checking as you go along and try to have some redundancy as you go along. It's definitely something you have to think about, yeah.
So that's actually a roll your own sort of thing. It's not in the infrastructure.
No.
So is there a checkpointing library you use, or you just wrote the restart files? Okay.
Yeah. They have their own restart files built into Flash, and they have it their own way. I mean, it's all done with this HDF5 big data structure sort of thing, but it's kind of specific to the code, basically. And every code has their own routine.
Are you using the parallel HDF5 stuff?
Yes.
Okay.
Yeah.
Cool. That's working out well for you?
Yeah.
What grid operating system are you using? Something open or dedicated?
I mean, I think they use Red Hat now mostly on the machines.
No, not the machines. Like Grid Engine, Slurm.
I have no idea.
When you submit the job, like PBS job or what?
Oh. I don't. What's the latest one they're using now? Slurm. Okay.
Slurm.
Yeah.
Okay.
Yes.
So I had a question. This is kind of slightly philosophical, because we got a philosophical system. So, in terms of science and doing these simulations, these sort of big computing things, can you comment on how that is changing science or not changing science?
I mean, it's totally. I mean, it's science. I mean, basically, it's become a new field of it. Like in the past, if you look at astronomy, at least, it used to be there were people who would look through telescopes and observe things, and there were guys who would sit down on pen and paper and write things out. If you're doing physics, there's also people who are in labs. So there's sort of three prongs. There's labs, theorists, and guys who are going out there and looking at things. But for us now, I mean, now that computation has taken off and these big simulations have taken off, it's sort of the fourth thing. I mean, we can't really reproduce the simulations inside of a star here on Earth. So being able to do this in a computer basically just lets us do something that we never, ever could have done, 30 years ago. On top of that, too, it's kind of changed the whole way, I mean, not just for theorists like me, but for people who actually still look through telescopes and use them, it's changed their job, too. Every astronomer nowadays is a computer programmer. We all, you see it on TV and it looks all glamorous, or in the movies, and we're all like wearing lab coats and walking up to the eyepiece and looking through the telescope. But the reality is all of my cohorts, even those who use telescope data, are actually just sitting in front of a computer all day, every day. That's what we do, it's sort of that kind of job. You do that because you're using, even people who are observing have very large data sets. Computers have totally changed the way we can do observing. We can have robotic telescopes scan the whole night sky, and then we run machine learning algorithms that go and pick out different targets and try to find, these supernova or whatever. I mean, it's just totally changed things. And we're kind of now in this era, we call it, this era of doing these large scale projects like this. I mean, it's totally just changed the way that we do astronomy. And, all of science, really. Green shirt.
What's a CPU hour? Because...
So it's using one CPU for 1 hour, or one core for 1 hour would be a CPU hour.
So how many cores are there at the Austin facility?
500,000. So now this math becomes a little more reasonable, right? Yeah, because you can't run. Clearly you can't run it on a local machine. Yeah.
And these are modern 4 gigahertz cores, etc.
Yeah. I mean, they're specialty cores. They've got all their sort of, and they've changed hardware. I mean, since I've been here, they've changed the hardware twice. Basically, what they use, they always try to keep as up to date as possible, and they work with the chip manufacturers to get very specific, their own custom chips, their own custom motherboards, all these kind of things. It's a really impressive facility they have out there. They're over on, they're out on like Breaker Lane. They've got a big tack. They have all these big, you'll see it, it's like across from the domain, there's like this big barbed wire fence. All the supercomputers are on the other side of that. It's a big impressive thing that they have set up there. But they do all their custom hardware, and they're, very much on the cutting edge and very advanced stuff. Yes.
How valid are the successful simulations that you have once that you prove a theory or
everything's in different stages. It depends. I mean, there are certain parts, certain people who simulate certain things are like the 100th person to simulate that, and they're trying to refine a small detail. But for simulating supernova, I am basically the first person to get one of these things to explode with all the physics in there. Nobody'd really done that. For other types of supernova, there's a lot of people who look at it, but they're still having trouble with the physics. They don't fully understand it and all that. So that's very early on, and nobody believes the results. I would say this now, me being the only person who's done this type of simulation, nobody believes my results really either. I mean, they're kind of like, oh, okay, that's interesting. Let's see what happens 10 years from now, sort of thing, So yeah, it's kind of all over the place. But there are other fields of things, like we understand now how stars evolve, and we can make really, really specific predictions on how stars evolve. And so the guys that do that kind of simulating, they can very quickly directly test the results, and we believe those very, very, very well. So it just depends on how long people have been simulating it, really. Yes?
how dependent is the total energy of the explosion on the angular momentum of the star?
That's one of the things I directly studied, not in this work, but in a different work. And basically, not that much, as it turns out. It's a bit complicated, but basically, if you have a lower angular momentum star, your black hole gets bigger because more stuff falls in from the beginning, which means you have more gravitational energy you can extract as stuff falls towards that bigger black hole, and actually your energy is end up being about the same. It's a very good question.
Even though the black hole is bigger? That strikes me as counterintuitive. I would thought the bigger black hole, then less energy would be output from the explosion.
So what ends up happening is it's a bigger black hole, so it has more gravity. So basically, all your energy really is just coming from gravity. So if you get a bigger black hole, stuff's going to end up falling in faster as a result. And so the faster stuff falls in, it's just sort of the more energy you get out. And that's something that, again, is one of these sort of just on the cutting edge speculative things and not something people really predicted beforehand, but it seems to be fairly robust. I tested with a lot of different angular momentums. There are some details there. There is sort of like a minimum angular momentum you need and that sort of thing, but we kind of already predicted that these had to be happening in rapidly rotating stars, and we already see these types of rapidly rotating stars out there. So we have some precedent for it.
All right, well, I have one question for everyone here. How many
people here have a science background, actually have background in science? We have a lot of, holy crap. So you're getting questions about angular momentum, right? Like conservation and all this other stuff. That's awesome. What a great crowd. Well, thank you very much. It was a great talk. Very interesting. Yeah, all right, well, I guess the obligatory, how many Fortran? How many have any Fortran? Well, see? How about IDL? I think you already asked about IDL, right? Yeah, look at that. AT back there, awesome. How many Java? Maybe you have a background in Java. There you go. No shame. Just all right. So I've got good news, which is that sort of the existence. We'll talk about existence, and we'll talk about well, I guess not uniqueness, but the existence is that the good news is the pizza is coming. So we have existence. However, from a timeline perspective, it might be still at this point, another 15 minutes before it gets here. Which is, I think, Aaron, if you're ready to go, yes?
You mentioned uniqueness. Does that mean there's only one pizza?
There's only one set of pizza. However, there are, I believe, 14 pizzas, so I think we're going to be okay. Or maybe 16, so we'll be all right. But hey, how did everyone like the chicken last time? How many people here had the chicken? Here. Yes? No? Should we do it again?
Yeah.
Yes.
Yes? All right, how many vegetarians? Okay, and how many non-beer drinkers? Okay, good. All right, very, very good stuff to know for plan. All right, thank you. So Aaron, if you're ready to go, just look up to the air display, and it's co-working.
Did it get closed back in?
Oh, we need to be on the,
life science tends to take over.
Say what?
The life size thing tends to take over.
Life size?
Life size.
Oh, life size, yeah.
I mean, all you need to do is be on the internal network.
Yeah, I know. So what's the name of the co-working?
Not on HDMI.
No, it's good. This is going to be Apple TV. It should be.
Yeah, that looks like he's there.
There it is. All right. And awesome. There you go. Yeah, if you want to grab like a refresh on the beer, there's still plenty of beer in the cooler. This talk, I think, is going to be one that's more lively if lubricated. Yeah, well, okay. I mean, all right, maybe I should have said that. That's the beer talking. All right. Here you go.
Take my beer bottle away from me.
Okay, so I forgot to put my name on here, but I'm Aaron Meurer. I work for Continuum. I believe we're hiring?
Yeah, sure.
Sure, we're hiring. Talk to Peter if you're interested. And so just a quick survey. How many people here use Python 3? 1, 2, 3.
Look at that.
So last month there were 3 of us.
10 now. Yeah.
Which was very embarrassing. And there was earlier a lot of laughing about how nobody uses Python 3. And so now I'm going to prove that we're going to have the last laugh because here are 10 awesome features of Python that you can't use because you refuse to update to Python 3. Or, as suggested, turning it up to 11. So real quickly, last month, I hope people can read that. Because I'm pretty sure it's impossible to phone.
Command plus. Okay, hold down Control and mouse wheel up.
Yeah, so that Command plus just like.
Yeah, hold down Control and mouse wheel up.
Okay, I gotta get my mouse wheel up.
That's turned off?
Yeah.
It's turned off by default in like a newer release.
Ah, that's like the best feature.
Yeah,
Almost
I
10.
was pretty upset.
Lord.
You can turn it on, of course. But
What is this? What technology are you using Python 3 for this presentation?
Yeah, it's just zooming my monitor. It's not zooming the display.
Oh, okay.
So yeah, this is just some library I found to do slides, which apparently doesn't support increasing the font size. Can people seriously not read this at all?
I think it's really hard back. Yeah.
read the slide.
Okay, well, I will just read the slides, I guess. So there are a lot of new features in Python 3. Some of them have been backported, like the print function or set comprehensions. But there's also a lot of features that haven't been backported, and I think a lot of people don't know about them. And these are features that you can't use if you have to support Python 2. There are syntax changes, there are interpreter behavior, there are standard library fixes, and it's more than just the bytes Unicode thing that everybody likes to talk about. So I just added this the other day. Feature 0, which is feature 0 because you can't actually use it yet, is matrix multiplication. There was a PEP accepted Monday, I think. Now instead of typing np dot AB in Python 3.5, you'll be able to do A at B, and that'll be matrix multiplication. So if you guys use matrix multiplication in NumPy, here's your reason to upgrade.
But we can overload the.
Yeah. So any object. So nothing in Python itself will overload this by default, but you can overload the matmul method on your objects. And
what this means is that now Twitter handles are now valid Python.
Yes. Yes, and so are emails.
Yeah.
So you can write an email library where an email actually creates the email address.
And it does the database access, it doesn't make it.
Can you chain it? Yeah, I mean it's just an operator. You can basically make it so that your object at any other object creates whatever you want. Okay, so the next feature, we all know about unpacking in Python. You can do A comma B equals something, and that'll, if that's like an iterator, that'll unpack the first two values. But what if instead of range 2 you had range 10? You don't want to do A, B, C, D, E, F, G. I don't know how many letters there are. So in Python 3, you can just do A comma B comma star rest, and that'll just dump the rest of whatever the iterator is into this rest thing. So here A is 0, B is 1, and rest is the list of 2 to 9. And rest, the star rest can go anywhere. So you can have A comma star rest comma B, and that will give you the first and last item and dump the middle bit into this rest, or you can just have it at the beginning. So imagine in Python 2 getting the first and last lines of a file. How many lines of code would that be? So here's it in two lines. First comma star underscore comma last equals f dot read lines. So here we have the steps using Python to profit. First step, use Python 3. Last step, profit. Another interesting thing you can do with this is easily refactor your function. So if you're using star args in your function definition and you decide you don't like that, you can just move that down a line and replace everything. Just put this, the old function parameters equals the new function parameters, and that will work because of this new syntax. I just realized that when I point to something here, you can't see it because I have a mirror.
You can set your screen resolution down. Can I try that?
Sure.
It really is hard to read.
Yeah, sorry.
Spotlight displays.
Yeah, displays. Okay.
Or Alfred, if you're cool.
Quicksilver, actually.
There you go.
Those are
Okay.
just gonna make it worse.
That's the smallest one, right?
No, don't click it. Don't click it. Wait, isn't there? You can't.
With the AirPlay stuff, they've really limited it.
I can plug in.
So we have a room full of programmers, and we can't make the font bigger. Can you go to? Wait, this is in a browser, right? Can you go to DevTools and just edit the CSS? And just change the font size?
No,
I'm serious. Like,
that's totally possible. But
yeah,
CSS, I totally don't.
Yeah, we can do it.
You could just turn on the Zoom feature. You are in the
that's true.
No, it doesn't work. It like
it zooms the screen, but not the other.
It zooms. It like the CSS forces the font.
Right, that's bigger.
No, go to the control panel. Go to the control panel and just turn on the accessibility so the control panel.
No, it does.
No, it doesn't work.
On
It doesn't work on Air Display. It's all Air Display. I can plug in.
Give it a few years. We'll figure this out.
Okay.
So maybe. All right. Never mind. I'm sorry. I didn't mean to derail your presentation.
Okay. Well, that didn't work. So you're just gonna have to imagine it in your head. Also, this is online. If you guys have laptops, you can go to. There's a whiteboard here. I can write this down.
Hit Control and zoom up.
No, it doesn't work. It doesn't work on the Apple TV.
Can you just open? Can you just
Yeah.
open? Can you just open the Word text file and just copy it there, and that's it?
Yeah.
Can you just
Oh, sure. But I've got images.
Oh.
I mean, you won't be able to see my internet memes.
No,
if
you can switch in between, but open the web, open the browser.
Then it can probably play.
All right. I'm gonna call point of order. Let's just let Aaron get on with the presentation.
Okay. So the URL is there's 72 slides. 72. Here, this is the URL. I know you guys. Okay, so the irony of that occurred to me after I said it.
Mark.js.
Yeah, so how do I?
GitHub, Python 3.
Aaron, just copy
something.
Just copy paste it into a Word file and then
Yeah,
make it
highlight the whole
bigger.
thing. Control C and Control V into Vim. Vim will save us all.
Can we just plug it into the TV? That's Aaron ASME, the low tech way.
Crazy?
Figure it out.
Woo! So Remark.js is the service you're using?
Mm-hmm. Yeah.
You would highly recommend for.
Well, it doesn't support font resizing, but it's pretty cool. You can just write Markdown in an HTML file, and it just works.
How do you have a QR converter?
A what? A QR code?
Yeah.
No, that's way too complicated.
Okay. There's a Python library for that. Next time.
All right. So everyone got that?
Okay.
Okay. There's another TV right there, so not all is lost. You're aware, right? There's no TV right there.
Oh, okay.
Still.
It's still too small?
Okay.
You can't even see it? Anyway, this is my favorite feature, keyword-only arguments. So you all know you can have, in a function definition, A, B, star args, and that star args will collect all the additional arguments. Well, now in Python 3, you can put after that a keyword argument. And so basically the only way to access this keyword argument is to explicitly call option equals true here, because it comes after the star args. So if you do something like this, there's no implicit third argument. The keyword argument becomes a third argument or anything like that. And if you don't want to collect star args, you can just write A, B, star, option equals true. And so so now there's no more, oops, I accidentally passed too many arguments to the function, and then one of them was swallowed by a keyword argument. So here I have my own little sum function, sum ab, byte me equals false. If byte me shootil.rmtree / else return a plus b. So sum of 1, 2 is 3. Sum of 1, 2, 3 is not good.
Yeah, we wouldn't have gotten that.
Huh?
We wouldn't have gotten that more.
No, we wouldn't have. You would have just seen the link.
Right.
You'd have to imagine it, which is what you have to do with the text. So, would you rather see text or images here? So in Python 3, you can just write the star here, and now you have to explicitly call byte me equals whatever if you want to be bitten. And if you just do sum 1, 2, 3, and it says no, it takes 2 positional arguments, but 3 were given. So, much better. Another scenario is I reordered the keyword arguments of a function, and now I broke everything that used that function because I was just passing in the keyword arguments as additional arguments. So here's a nice little utility function that I wrote recently. Max all, it gives a list of all the maximal items from the iterable, and like the max built-in, it takes a key function. So max all of this list of strings with the key equals len are these 2 strings that have maximal length. Here we go. But the max built-in from Python supports not just passing in a list like this, but you can just pass in the arguments one at a time. So the way we would do that is pass in star args, and then just check if there's one argument or if there are multiple arguments. But the problem now is we just broke the code that was passing in len as the second argument. Now it thinks that we want to know the maximum of this list and len, and it says we can't compare lists and functions, which is actually another thing we'll talk about later. And so actually this kind of shows that Max already does this in Python 2. The len parameter, you have to pass it in as len equals, right? So, but Max is written in C. And so if we'd used iterable star key equals none to begin with, we would have future-proofed this code because nothing would have been passing in this parameter implicitly, this keyword argument implicitly. We would have to call key equals len. And so another way we can make our APIs future-proof with this is, so here's another stupid example. We have a shorter list and a longer list, and we want to extend the shorter list to the same length as the longer list with a value. So we have def extend to value shorter longer. And so A is 1, 2, B is 1, 2, 3, 4. We extend A to the length of B with the value 10. We get 1, 2, 10, 10, 10. But maybe I wanted longer to come before shorter in the parameter list here. Maybe that makes more sense. Extend to value longer, shorter. Well, that's too bad, because you already used it. You're going to break all the code that uses it. Python 3, you can make these keyword arguments, and now you have to pass in shorter equals whatever, longer equals whatever. And if there's a point of contention, you don't like that order, then you can just pass it in as longer equals whatever and shorter equals whatever. And so you can, the great thing about these keyword-only arguments is you can add new keyword arguments anywhere in the parameter list without breaking the API. And for example, in Python 3, there's all the, or a lot of the functions in the OS module and have this follow symlinks option. So instead of using OS_lstat, you can use os.stat file follow symlinks equals false. And this is implemented using keyword-only arguments. And this basically keeps you from thinking that it's a 2-argument function on accident. In Python 2, if you want to do this, you have to use star keyword args and put all the logic at the top of your function. You have a lot of ugly keyword args.pop to get the default thing. It's no longer self-documenting because the default arguments aren't there in your parameter list. So if you're somehow using Python 3 only in your code, I highly recommend using this for all your option keyword arguments. Okay, feature 3, chained exceptions. So you catch an exception with try except, and you raise a different exception in the except block. So here I have my copy, and I try to copy 2 files, and if there's a permission error, I erase not implemented error, automatic pseudo injection. And so I try to copy 2 files that don't have the right permissions, and I get permission error, automatic pseudo injection. And so what about the OS error? That's what I was catching here. What if I want to know what happened, what actually happened to go wrong here? So in Python 3, you can see the traceback for the exception that you were raising, and also the traceback for the exception that was caught. And this chains indefinitely. So you can see I raised not implemented error, but that came from handling the permission error. And you can do this manually using raise from. Yes?
So you say that Python 2.7 cannot do this because you can raise an exception within an exception.
You can raise an exception within an exception, but you don't know what happened to the original traceback of the exception that you caught.
But you can save it somehow, no?
Oh yeah, you can like tear it off of the exception object or use sys on the traceback or something. I mean, it's a lot of extra code. Python 3 just happens automatically.
Okay.
Every traceback is chained automatically.
So you don't have to call sys.info, you just get it.
Yeah, you just get it. I mean, you get the whole chain, even if it's some code that you're not even in control of that caught the exception.
So what if we want to hide our trace?
Well, if you want to hide your tracebacks, you don't raise the exception. You just use bare except, and now all of your errors are hidden from you and your users.
You say that a little more constant.
I mean,
no more errors.
Don't raise something good. We want
So exceptions should not be silenced. How does there's something in the Zen of Python about this, I think, about silencing exceptions. Import this. Okay, so the code I just showed you was actually wrong because OS error means a lot of things, and I just implicitly assumed that it means permission error, but OS error could mean file not found, it could mean you broke a broken pipe, it could mean you passed in a directory when you were expecting a file. So what you really have to do is import this error-no module, look up the magic error codes, which for permissions are eperm and eaccess, and then when you catch the error, you have to check e.errorno if it equals one of these 2 magic error codes. And if that's the case, then you have a permission error. And if it's not, then you have some other kind of error. And so basically, this really sucks. If you've ever used Python to do file system manipulation, you're either catching errors that you shouldn't be because you're not checking these error numbers, or you just have a whole bunch of boilerplate code to check this. So in Python 3, this is much better because we have subclasses of OS error. So now if there's a permission error, it'll raise permission error, which is a subclass of OS error. And so this permission error is basically a replacement of these 2 error codes here from Python 2. And everything's backwards compatible. Those error codes are still there, so code will still work. But instead of having these 4 lines to check if it was the right error, you just had it catch the right error. Feature 5, the one a lot of people probably know about, everything is an iterator. This one's, I think, kind of hard to sell. We have iterators in Python 2. We all know about xrange, right? Everybody knows about xrange. But you kind of have to use them. I mean, you have to remember to write xrange instead of range, or izip instead of zip. And so if you just use range, so here's a naive way of summing the first n integers, which is actually naive not because it uses range, but because there's an explicit formula for it that computes it in O1 time instead of On time. But anyway, I'm just going through the first n integers using range n+1 and adding to an accumulator and then returning it. And so I decided in Python 2 to just time this to see how long it would take. So first million integers takes 61.4 milliseconds. First 10 million integers takes 622 milliseconds, so it's still pretty fast. And then I tried 100 million, and I got this. This was on a computer without a whole lot of disk space free. But OS X likes to just convert RAM into virtual memory, and just whenever you use too much memory in Python, you'll just run out of disk space. So basically, if you use range in Python 2, you're going to have a bad time. So of course, we all know the solution. You should be using xrange or itertools.izip or dict.itervalues instead of dict.values, which is a little inconsistent, right? You just have to remember to put an x in front of it if it's range, or an I in front of it if it's zip or map, or an iter in front of it. Well, Python 3 gets rid of all this nonsense. Everything is an iterator that should be an iterator. If you want a list, you just wrap it in list. Explicit is better than implicit. It's hard to write code that accidentally uses too much memory because you forgot to use the iterator, and your input was bigger than you expected. Okay, next feature, feature 6. Am I timed, by the way? Is there time that I need to worry about?
The pizza is it's not so much the time, it's the existential aspect of the pizza.
Oh, so if I go too long, there won't be pizza left for me.
No,
or do you want to take a break and come back and
yeah, I think we should take a break.
So we are halfway through. If you want to do a break, that's fine with me.
Let's just do that real quick and we'll come back. And let's see if we've solved the font problem.
Okay.
Well, everyone's going to do this.
Okay, everyone. Now we'll have the pizza. Well, and we've also, there's great news, we fixed our font problem.
So the secret, if you guys are interested, there's this accessibility option, never show font sizes smaller than X, and it'll just refuse to show small fonts. Okay, so I think we only have 20 minutes, so I'm just going to carry on, and if people want to see earlier slides, just let me know at the end if we have time. Or if there are any questions about what you've seen already. All right, well, feature 6, no more absurd comparisons. So in Python 2, you can ask which is bigger, 1 or 2, and 1 is bigger than 2. The string ONE is bigger than the number 2. And so, yeah, I just proved math here. I just disproved math. So in Python 2, you can compare everything to everything. You can compare strings to numbers. You can compare none to functions. And in Python 3, you can't. It'll just raise an exception unless it makes sense. So you can compare strings to strings, and you can compare numbers to numbers, but you can't compare strings to numbers. I hope things aren't like going off the bottom of the slide here with this font thing.
They are.
They are.
Isn't there a way to disable it if you want to go back?
It's still better.
It's still better? I don't know what's below that. It might be nothing.
It says in Python 2 there's a sorted function.
In Python 2 there's a sorted function?
Here. Sorted? Here's the unadulterated.
Oh, well, yeah, okay. So the problem with this implicit comparison is if you sort a list or use max, and then it's using these comparisons implicitly. So if you accidentally put a string in a list that you expect to have numbers and you sort it, you'll get sorted like string 1 and then the numbers 2 and 3, and it'll compare the string 1 as greater than the numbers 2 and 3. And so the sorted list will be 2, 3, string 1. And so, I don't know, this happened to me several times, and you have something that you expect to all be integers or all be strings, and somehow one of the other ones slips in, and you just still sort it, and you get odd results. Okay, so now we're starting to get into the area of I promised 10 features. Yield from, how many people here use generators? Oh, cool. Well, yield from is actually pretty awesome if you use generators, because instead of writing this for I and whatever, yield I, where the whatever is just some function, you just write yield from the function. And so it's really easy to refactor your generator. Just pull a piece of code out into a function, a subfunction, and just yield from that subfunction. Oh, so we can't see the best one here. We can see bad and good, but there's a better. So, you know, the reason generators are awesome, you know, you can maybe just take a list and extend things to it, or you can yield I. This function takes n and returns like 0, 0, 1, 1, 2, 2, 3, 3. The better version is yield from the list II. So generators are awesome because they're like basically the same reason X range is better than range. You have low memory impact. You're only computing one thing at a time. If you don't need the whole thing, you can stop in the middle without computing the things that you didn't use. If you still need a list, you can just still get a list just by calling list. And also the function state is kind of saved between yields, which leads to interesting and difficult to understand things like coroutines, which also leads to difficult to understand new standard library features like async IO. So Python 3.4, this is from Guido's presentation. Okay, so I'm pretty sure I need to make the font smaller for this one. Don't worry, you wouldn't understand it if you could see it anyway. In fact, in this presentation, Guido basically just says, you just have to squint. Pretend like the yield froms are there, but you have, you know, while yield from r.readline, and so basically this is pulling things in from the internet asynchronously. Each of these yield froms happens asynchronously. And so I'm not gonna lie to you, I don't get this at all, but it's okay because David Beasley also doesn't get it, or at least had a hard time getting it, and he basically wrote the book on coroutines. Okay, now I should probably... Okay, so feature 9, some neat things in the standard library. Let's make this a little bigger again. Fault handler, so you can just run this fault handler enable, and this will print a limited traceback even if your Python code dies really hard, like a seg fault or an abort. So here's the example. I'm seg faulting the interpreter using C types, and I get a limited traceback here telling me what lines were being run. And you can also run this with -x fault handler, Python-x, capital X fault handler. And so if you've ever had code that you've had that keyboard interrupt doesn't work, you can send it a sig abort, which is kill-6, and it'll work with this fault handler. Another one, a new one, is IP addresses. It's just IP addresses. Just another thing you don't want to roll yourself. This one's really cool. If you guys ever cache your functions with little decorators, this is now built into the standard library in Python 3. So functools.lru cache, and it does the right thing. It's actually LRU, which is what caches typically should be. It doesn't just grow infinitely like your naive cache probably will if you just roll your own. And you can also, it has these nice features. You can profile things. It'll tell you how many cache hits you've had, things like that.
Can you explain a bit more about this?
So LRU stands for least recently used. So you have a fixed cache size here, it's 32. So every time you call the function, that value is cached. The result of that value is cached until there are 32 items in the cache, and then the least recently used one is tossed out of the cache, and the next one's put in.
The last functions, like the code of the last.
The last call, input and output is all that matters. So if I call this function with the input of 8, and it returns the URL for pep8. And so the next time I run that, it doesn't have to go to the internet and try to find that URL. It's saved in the cache, so it can return instantly. We finally have enumerated types for the standard library in Python 3.4. And this is actually using some magic features of Python 3. So let me see if I can, this probably won't show if I make it bigger. Oh, you just don't see the error. So take a look at this. I've got class shape, subclass of enum. I'm setting square equals 2 and square equals 3. And then what this does, very magically, so think about this code. I'm just defining square equals 2, and then the next line I'm overriding what I just defined. So normally this square equals 3 would just override the square equals 2. But Python 3 has some new metaclass magic that lets it basically say, no, you define square twice.
So what is the metaclass magic it's using?
It lets you create a custom dictionary subclass that's used to gather in the attributes of the class when the metaclass begins. So you can use a subclass of dictionary that doesn't throw away the old thing when you put the new thing in. You can use a default dict list kind of thing, and then keep track of that.
The only way to do this in Python 2 is using set profile hook, essentially.
A profile hook?
Yeah.
You'll have to show me that later.
So I do have a question. I mean, traditionally in Python, constants are done in uppercase. So enums you've used here are not.
This is straight out of the docs. So
this is kind of.
I mean, that's yeah. I mean, I just pulled this straight from the docs for the enum module. So if you think enums should be constant in Python, then go open an issue to change the docs.
Well, no, I'm just trying to say.
But these enums aren't integers. They're not like C enums. They're actual.
You mean they're namespace inside?
Yeah, they're basically namespace, but they have these nice features that I can open the docs.
Remember, constants are only capitalized because we choose them to be capitalized.
Well, we also don't use absurd camel casing in Python like Java does. So.
Well, but we've chosen to do uppercase for constants, and enums are a variant of constants. Why do you think they've gone to lowercase namespace, lowercase here? Because it's a style question.
It could just be because this is a class. Are you talking about the class name or the attributes of the class?
The attributes.
I mean, this is just pep8. The class is camel case. The attributes are lowercase with underscores. It's not as, I mean, enums are just another class in the standard library. There's nothing syntactically special here.
I think the key thing is that red doesn't pollute the global namespace.
I got that. Explicitly. I got that. The question is really a convention question.
Oh, okay.
Yeah. I don't know if there's anything in PEP8 about enums. I mean, it may have been discussed. You can look up the PEP that introduced this and see if it was discussed in there. So last feature, some fun things. You can now use Unicode in your variable names. So resume with the correct spelling equals knows Python. Pi equals math.py. Bad news, letter-like only characters. So beer equals beer, that doesn't work because this is not a letter. This only works because, believe it or not, pi is actually a letter in some languages.
What about Chinese? Yeah.
Only if it's letter-like. There's a specific definition of that in Unicode. And I don't know Chinese, so I can't actually test this. But those of you who do, I encourage you to test and report back.
I can try Hebrew.
Oh, Hebrew should work. I don't know what Chinese is considered to be letter-like and what is not.
How do they handle the right and left then? Without
encoding. So basically, a lot of people hate this feature because now you have variable names that nobody can type. unless you have a special keyboard. No, I don't think. I'm pretty sure no. You'd have to check, but I think you just have to use regular dash and underscore. I could be wrong about that. But the definition is letter-like, and if you're doing a regular expression to catch a variable name, there's some thing that'll catch all letter-like characters.
I didn't even thought about that. This would break all those things.
Yeah, if you're just doing AZ, that's wrong. But there's a magic thing you can use in regular expression to catch it correct. Well, I mean, your regular expression's wrong anyway if you're not using the keyword module to not get keywords. You know, AS is not a valid Python variable name.
So let me get this straight. There are now about 20 different distinct variable names that all look like a single circle.
Oh yeah, I mean you can have Cyrillic characters that look exactly like Latin characters.
Ouch, 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 ouch.
I mean this is great if you want to troll people.
Oh right, because as spelled with
Aren't you trying to persuade us to move to Python?
Oh well, this is feature 10 equals fun. I like I said, I promised 10 features and I had to get 10, you know. And I didn't want to talk about async IO, you know, because that's insane.
Oh, just to go back, so back up to the async IO thing, and then the phone, yeah, right there, right? So I think one way to think about, how many people here have used yield from? I guess it was a subset of Python 3 folks. How many people have used yield from? Or feel like they understand?
Well, all right, who is using Python 3 again? Are you using only Python 3, or does your code have to be Python 2 compatible? Who's using only Python 3? So 3 people of what, 10? Yeah, I counted 1, 2, 3.
Well, Andrew got Andrew's hand up. That's 4.
Where's the 4th?
Oh, you counted Andrew?
Yeah, I counted Andrew and 2 guys over there.
Was that 0 indexed or was it?
No, I'm a mathematician.
Sucks that you're gasping.
Well, so my question was that with the yield from, would it be accurate to say you can think of yield from as a different kind of method invocation altogether, right? Because it's invoking preserving closure, like not stack-based invocation, essentially, almost like stack.
Yeah, there's some other magic you can now return inside a generator, and that does some magic things if you're using coroutines.
Yep.
I mean, who understands coroutines? There's 3 people who use Python 3, and 1 of 2. How many support coroutines?
3 coroutines. Yeah.
Yeah. So there you go. That's why that's feature 8 instead of feature 1. These features are in order, the order I like them. But the other fun feature that is actually fun is these function annotations. This comes at the end because they're a little misunderstood, I think. Python doesn't actually use these to do anything except keep track of what you put there. So you can put, in your parameter definition, you can have these little colons after the parameters and have magic things, and you can also have one for the return. And all this does is put it in the Dunder annotations dictionary of the object. But this leaves open a ton of possibilities. You can have libraries that do type checking. You can have these new IPython 2.0 widgets, which, let's see if I can...
What about Cyphon? Something that Cyphon can read out of this.
Let's see if I can get this to work live. There's an example. And fortunately, IPython 2.0 has reasonable URLs, so I can hot link to a notebook that didn't exist until I just ran it. Okay, so I don't have a scikit image installed. Crap, should have tested this on laptop.
Now I gotta build scikit image.
Oh no! If only there were a binary package manager that would let me install Python scikit image immediately.
If only we could see what you were doing.
Oh shit. If only I weren't on an experimental branch of that package manager. Okay.
I didn't believe you.
How many people here have seen IPython notebook widgets? Okay, not very many people. Okay, so this is.
But now, since it's the same URL, I should be able to reconnect, right? How many of you guys use IPython Notebook? How many of you guys have tried 2.0? Let's try reloading the page. That's not Shift-Enter.
Great.
Okay, so this is going to be hard to do. There's these widgets now. You can interact with things. I think that's the uninteresting one. So I can turn down all the red on this image. Let's turn down this sigma too. And so this is what this image looks like with only green and blue. And you basically take the function here and you write these interactive. You create this interactive object basically with the parameters. But it's kind of annoying because here's your function and here's like the sigma parameters. They're kind of separated. So Python 3 annotations let you inline that. So now sigma, it's just telling you right here what the parameters need to be for this interact. And I just have this decorator. And so like here, I'm just saying that G has these limits up here. I'm assuming that means from 0 to 1 with steps 0.1. And it's the exact same. So I can turn on the green. And so this is a much cleaner way to use these widgets with these function annotations. Okay, now I have to figure out how to get back.
Reload.
Gotta open something. Yeah. Okay, well, we were going to turn it up to 11, so feature 11 is Unicode and bytes. Everybody's favorite. So Python 2 stir kind of acts like bytes of data, almost like a C string, array of characters kind of thing. And there's also a Unicode type to represent Unicode strings. In Python 3, stir is a string, meaning a Unicode string, so you do actual string operations on it. And then if you want to actually work with bytes of data, there's this bytes object. And there is no Unicode, everything is Unicode and just by default. And so now this is the part where I hide and you discuss bytes and strings. But yeah, seriously, any questions or discussions? I think we have 0 minutes left, so.
Might have to continue at the bar.
What?
Might have to continue at the bar.
Continue at the bar, right.
Yeah.
Yield from, wait. So which bar are we going to, Travis?
We can talk, not noisy.
Chicago House.
Bar?
Chicago House?
It's always good.
Yeah, worked out last time.
Where is it?
All right. Well, thank you, Aaron, for very excellent.
So before we, just as we adjourn, please take your bottles and put them in the recycling back there. Any pizza plates, please dispose of them in an orderly fashion. I want to thank our sponsors again. The Capital Factory, as always, very kind to provide us a space. And then also steeprockinc.com if you guys, oh, and validation, parking validation tickets. If you parked in the parking garage, get them from Ollie back there at the desk. We're going to Chicago House, which is at...
It's between 7th and 6th on Trinity.
Okay, it's on Trinity between 7th and 6th. So I'll see y'all there.